You're watching a Channel 98 NBISD TV production.
I got the whole world. Hey, welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Where would we be in the world without mathematics, right? I know you're asking that. Well, mathematics is very important. Today we're going to be talking about parabolas, kind of an extension of last week's show. We're going to finish it up, and I'm going to show you how to calculate with a little ball, without actually having to throw it up, how long it's in the air, how long it takes to hit the ground, and how fast it's going when it hits the ground. So stick around, download those worksheets from the district website, and let's learn a little bit more about parabolas today, shall we? All right, welcome to Lesson 12. We're going to kind of finish up what we started last week with some transformations. Then we're going to move into a very important topic of finding x-intercepts. All right, so last week we covered the shifts, which were the horizontal and vertical translations. Those came from addition and subtraction. If it was added to the inside on the x, it was a horizontal. If it was added to the outside or subtracted to the outside, it was a vertical shift. So inside is always x, outside is always vertical. Today we're going to look at multiplication, which is going to be two special types, reflections and dilations. So here's the first type. We're going to look at reflections first. There's two varieties. We have a reflection across the y-axis. Now, if we're going to reflect across the y-axis, what we're going to do here is we're going to take our x values that are positive and our x values that are negative, and we're going to exchange them. So instead of at 2, we're going to graph it at -2. And instead of at -3, we're going to graph it at 3. So the way we denote that is by replacing inside the function where we have an x, we're going to replace it with a negative x. So if I plug in a negative x into the squaring function, I get negative x quantity squared. Now notice what happens. This is my original function, y equals x squared. If I was to reflect this graph across the y-axis, I would not see any change in the graph, and that's because this function itself has y-axis symmetry. Remember, the axis of symmetry is x equals the x-coordinate of the vertex. So in this case, we call this function an even function. An even function means it has y-axis symmetry. So we're not going to see that transformation. The other one is going to be a reflection across the x-axis, and the x-axis is when the y values exchange. So instead of a positive function value, I'm going to have its negative counterpart, or instead of a negative function value, I'm going to have its positive counterpart. So because it's affecting the y values, it's going to take place on the outside. And it's multiplying basically all your y values by -1. So notice by placing the negative outside the function as opposed to inside up here, I'm doing the order of operations. Pick an x, square it first, so now you have your y values in your hand, and then at the last minute, you're going to take the opposite of them. So if this blue graph is my function x squared, then all I have to do to generate negative x squared is reflect this graph across the x-axis, and I get this function down here, which is in red. Okay? So it has basically the same vertex, 0, 0. It's just opening down, kind of like a frowny face. Okay? And it has the same aperture. It opens at the same width. It just opens down. Okay? So that one we do see. It's a negative on the outside. The y values or the outputs are exchanging, versus a reflection across the y-axis. Your input values, your x's, are exchanging. Those are two very important types of reflections. All right, let's look at a dilation, which is going to be a specific type of multiplication, but it's not going to be by -1. What if instead of multiplying the entire function by -1, I wanted to multiply it by like a 5 or a 1/3 or something like that? Those are going to be dilations. Dilations kind of implies that we are changing the shape of the graph, not its location, but the shape of the graph. We're dilating it, kind of stretching it and compressing it. Well, let's look at, first of all, our vertical dilations. So we're looking at the parent function x squared, which is, again, down here in blue. It's this outer one. And what I want to do is I want to multiply the function by some number a. And we're going to assume that a is positive. It's greater than 0. Well, what happens if a is greater than 1? For example, right here, if I look at modifying my x squared function by putting a 2 in front of it, think about what this happens. This is pick an x, square it first, so you have all these blue y values, and the last thing you're going to do before you sketch it now is you're going to double all the y values. So look what happens down here. A y value at x equals 1 used to be a 1. Now we've doubled it, so it's up here at 2. A y value at 2 used to be a 4 on x squared, but if you double it, now it's way up here at 8. So these y values are moving upward, and they're not moving up by the same amount. Notice the origin doesn't go anywhere. That is in effect making the graph steeper. We are stretching it vertically like this, symmetrically on either side of the x-axis by a factor of 2. So notice that that's going to give us a graph that hasn't really changed the location. It's just changing its steepness. Okay? So multiplying by something that's greater than 1 on the outside is going to be a vertical stretch. That's what we'll call that. Vertical stretch, meaning that it moves away from the x-axis. Now, what if I multiply by a value of a that's still positive, but now between 0 and 1, like a 1/2? Same principle here. We're starting with our x squared, and now before we graph it, we're going to take half of the previous y values. So here's our parabola x squared in blue. The output value of a 4 has now moved down to a 2. The output value of 1 has moved down to 1/2. And the output value of, let's see up here, 9 is moved down to 4.5. And so notice that all these values are moving down now, which effectively makes your graph a little bit wider. It opens up a little bit wider. But what we are in fact doing is we are now vertically compressing it by a factor of 2. It's half as tall. Okay? So that's what multiplying does. If it's on the outside, it's affecting the graph vertically, either stretching it away from the x-axis or compressing it down towards the x-axis. Now it does appear to make the graph wider and narrower as well. But we want to think of this in terms of vertical movement. So what about the vertical movement? Well, those are going to be horizontal dilations, and I'm going to call those B's. It's still going to be multiplying, because anytime we multiply, we are dilating, either stretching or compressing, but now it's horizontally. So it's like we're playing a accordion, maybe? I don't know, if you're creative. Well, here's what we're going to do. We're going to look again at positive values of B, because if B is negative, it's going to end up being the y-axis reflection that we talked about. So let's go ahead and look at this. Let's go ahead and take now and multiply our x right there by a 2. It's inside the function. So notice in this case, we'll choose our x. Before we square it, inside the function, we'll double the x value. If we're doubling the x values, we're changing the x values, and then we're going to square it. What that means is at x equals 1, it's going to have the same y value as x equals 1 times 2, or 2. The x value at x equals 2 is going to have the same y value at 2 times 2, or 4. So although it looks like it's going to stretch the graph wider horizontally, it's actually going to gather the values in. Okay, so if blue right here is x squared, the value at x equals 2 is now coming in here to x equals 1. The value at x equals 3 right here is now coming in to 1.5. So notice that it's moving inward. And so it effectively makes the graph a little bit narrower, very similar to stretching it vertically by a different factor. So again, like with the shifts, if it's inside on the x, it's going to be kind of the opposite of what it immediately appears. You're going to see double your x's, so you're going to think twice as wide. But remember, it's opposite. It's half as wide, or twice as narrow. Now, notice that just by rewriting this, 2x quantity squared is 4x squared. So I can think of a horizontal compression by a factor of 2 as the exact same transformation as stretching the graph vertically by a factor of 4. And that's very specific in this case for a parabola. So sometimes we can look at equations and just look at them in a slightly modified way. We get the equivalent graph, but depending on how it's written in the equation, it could be a horizontal compression or a vertical stretch. But either way, it makes the graph a little bit narrower. Now what happens if we look at a positive value of b between 0 and 1? Like this, 1/2 x squared. Again, it's multiplied, so it has to be a dilation. It's on the inside on the x, so it has to be horizontal. So if the other one up here was a 2 and it was twice as narrow, then a 1/2, you would think, naturally, half as wide, but it's the opposite. It's twice as wide. So if we go to this graph here, x squared is in blue. What we're doing now is we're saying, okay, the x value at 1 is now over here at x equals 2. The x value at at x equals 2 is now over here at x equals 4. So this basically makes the graph wider, or it stretches it horizontally away from the y-axis. All right, so that pretty much puts everything together, all the different types of transformations. Let's see if we can kind of sketch one here. All right, here we go. We want to sketch the graph of f of x equals negative 3x squared. Well, the parent function is x squared. It's the parabola. So it might help to sketch that first. So here we go. There's an x and y axis. I'm going to sketch in x squared right there with a vertex at the origin, trying to make it y-axis symmetrical, and that's going to be my frame of reference. Okay? Notice I don't have any marks on my x or y-axis, so that could be x squared. Let me go ahead and denote that by doing it in red. Now what we're going to do here is first of all identify what transformations we actually have. We have a negative 3x squared. Those are both multiplying. So remember that the 3 itself multiplied in front is going to affect the graph vertically. So it's going to make the graph 3 times as tall, a vertical stretch by a factor of 3. And the negative 1, essentially, which we're multiplying by the 3, is a separate transformation. That's taking the opposite of your function values, which is your y value. So that's going to be, remember, the x-axis reflection. Your y's are switching. Okay? So whenever we have a negative multiplier, you want to think of it as two separate transformations. A dilation, a stretch or compression, and a reflection. And it doesn't matter which order we do them in, because multiplication, whether it's reflection or dilation, a stretch or a compression, has the same priority level. So I'm going to go ahead and reflect it first. Why not? So what I'm going to do is I'm going to take my graph and I'm going to do the negative transformation, which is going to be out in front. So I'm going to take this graph and reflect it down. And so the origin is going to be the same, and it's just going to look like that. Now I'm going to go ahead and label that. That's an intermediate graph. That's negative x squared. And so that's my intermediate graph. This is a sequence of transformations. And now I'll take this graph here and I will stretch it vertically by a factor of 3. So I'm grabbing it like this, and imagine pulling these ropes downward. You're going to bring the graph in. It's going to make it a little sharper, a little more narrow. Now it's going to be 3 times. So how do we show that? Well, unless we're labeling the y-axis with points, we don't really have to show it. As long as we draw it relatively steeper than this x squared graph, it's going to be good. Now your teacher might have different expectations. If this was a negative 1 value, this would be a negative 3 value. If this was a negative 2y value, this would be a negative 6. They're 3 times further down. Okay? And I'm going to go ahead and label that as negative 3x squared. So there you go. This green graph is our final graph. It's a parabola that's opening down. That's 3 times as narrow. Got it? Little practice, I think you will. All right, let's take a very quick break, but while you're gone, think about this. What's the difference between a math teacher and a train? The answer when you return.
The odds of a child making it to Broadway, 1 in 11,000. The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking about parabolas today and applications of parabolas. So what is the difference between a math teacher and a train? Well, not as much as you would think. No, actually, a math teacher says, spit out your gum. And a train says, chew, chew. All right, back to the math. All right, so that's transformations. A little practice, I think you'll have them down. But another very important concept when you're talking about polynomials, whether they're linear or quadratics, is trying to find the x-intercepts of the graph. That is, where the graph crosses the x-axis. Now, those x-intercepts have multiple names. So let's go ahead and look at these mathematical synonyms, all right? The x-intercepts of the graph of the parabola. Okay, we've already talked about that. But those are also called the roots of a quadratic function. If you think of the x-axis as being the ground, then the roots would grow underneath the x-axis. And right there where it goes from above the x-axis to below is kind of where the roots start. Okay? We also call those the zeros of the quadratic function because the x-axis is also known as y equals 0. So that's going to be where the function values or the y values are zeros. So roots and zeros really synonymous. Or we call them solutions to the equation f of x equals 0. And that's again because your f of x is your y value. So they really all mean the exact same thing. X-intercepts, roots, zeros, and solutions to the equation set equal to 0. Got it? Now these are going to be generally kind of more difficult to find than the y-intercepts. Remember, for y-intercepts, all we have to do is we let x equal 0. And our functions are explicitly defined in terms of x. So when we plug in an input value of 0, the y value output's pretty easy to find. But x-intercepts, a little bit trickier to find. I'm going to show you a couple ways how to find them. The first one we're going to look at is factoring a trinomial. That is a parabola in standard form. So what we want to do is we want to find the x-intercepts or the zeros of this quadratic function. Now notice it's written in standard form. X squared, x to the first, and constant. So it's decreasing. We're going to do this one by factoring. The first rule of factoring is to try to look for a common factor. But I can't really, I'm sorry, I need to back up here. I need to set it equal to 0, to create the equation. Remember, we're looking for solutions to this equation. So let's go ahead and create that equation. Now what I want to do is I want to solve this. I want to know what values of x when I plug in will give me a 0. We're going to try and factor. And the first rule of factoring is to always look for a common factor once you have it set equal to 0? Well, there's a 2 that's common, so I'll pull the 2 out, and that gives me an x squared plus a 1x minus 6 equals 0. Now I'm going to try and work on this little trinomial. It is a product of two binomials in this case, and a method of finding it, well, we're looking for a product, two factors that give us a product of negative 6, whose sum is positive 1. Well, that's going to be x plus 3 and x minus 2. With a little bit of practice, you can revive that technique, which you had in Algebra 1. Now there's something called the zero product property, and it's very important. It says if you have multiple things multiplied together and they all equal 0, then you could set each of them equal to 0. Well, I have three factors. I have 2. Well, does 2 equal 0? I don't think so. How about x plus 3? Does it equal 0? Or x minus 2, does it equal 0? Well, this is not going to give us any solutions. 2 is not going to be 0, not even at Halloween. That's past anyway. How about x plus 3? Well, it's a little linear equation. We can solve that. X equals negative 3. And over here I get x minus 2. If I add 2, I get x equals 2. These, then, are my two roots, my two zeros, my two x-intercepts, or the two solutions to that equation. Now we know what the parabola looks like. Since it is an x squared, it is a parabola. Since the leading coefficient, a, is positive, we know it's going to be a smiley, happy, turned up parabola. And I know what the x-intercepts are. So here we go. I'm going to sketch a little graph over here. My x-intercept is negative 3, 1, 2, 3. So I'm going to put a dot right there. And the other one's 2, 1, 2. There we go. So I would like to have one more point to guide me through here. Well, that's where the y-intercept comes in. To find the y-intercept, we're just going to plug in a 0 for x. So that's f of 0. If you come up here, that's going to be a 0 plus 0 minus 12, or a negative 12. So if I come down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There it is. Now notice that that is not the vertex, because this is not halfway in between here. But it does give me another point that I can guide my parabola through. The vertex we could also find, if you remember last time, negative b over 2a. It should be halfway in between the x-intercepts, 1, 2, 3, 4, 5. So 1, 2 and a half, somewhere at negative 1/2. So anyway, I'm going to sketch this now. And it's going to drop down, and then it's going to come up and look like that. And notice that by putting the y-intercept here, it kind of gives me a point so I can see exactly how far down I have to go, which will tell me essentially when I connect all three dots how wide it is. All right? This is basically a vertical stretch by a factor of 2. That's what the leading coefficient tells us. So that's not so bad. But notice factoring allowed us to get two x-intercepts, which are very nice points that we could find on the x-axis. Okay? Here's another example. We want to find the roots now of the following equation. Well, finding the roots, again, is finding the solution to that equation. So I'm going to set it equal to 0. Now notice in this case, it is written in standard form, but it's not a trinomial. I have an x squared term and an x term. I don't have a constant. And so it's not going to really factor into the product of two binomials. Again, the first step is to look for a common factor when it's equal to 0. There's a common factor of a negative 3, or just a 3. I'll pull out the negative. And there's also a factor of x. So this has a variable. In the last problem, the constant didn't have an x, so we couldn't pull it out. So if I factor out or divide out a negative 3, oops, I say a negative 3, but I just remembered, and I'm sure you caught me at home, I just said it had a negative 3x that's common. So let's go ahead and factor out the negative 3x. When I factor it out of the leading term, I'm left with just a single x. Now when I factor a negative out of a negative 9x, I'm left with plus 3. Now, a real quick check here. Distribute this back into both terms. Negative 3x times x is negative 3x squared. Negative 3x times positive 3 is negative 9x. So it works. Well, now I can set each of these three factors equal to 0. Negative 3 equals 0. Get a good laugh out of that. That's not going to work. Or x equals 0. So that's easy to solve. There's one of my roots. Or x plus 3 equals 0. That's easy enough to solve. I get x equals negative 3. So notice it's a parabola. It's a quadratic. It has two x-intercepts. I see a pattern emerging here. Now we want to sketch it. So let's go ahead, draw a little x and y axis. Our roots are x equals 0 and 1, 2, 3, negative 3. Now does this parabola open up or down? Notice the leading coefficient is less than 0, so it's going to be one of those downturning frowny parabolas. Okay? And I already found the y-intercept. Since it passes through the origin, that is a y-intercept. So I'm just going to go ahead and sketch it. I'm not going to even label the y-axis. So it's going to go up, turn around, halfway in between there, and come right back down. Remember, exactly halfway in between here is where you want your vertex, because that's where the axis of symmetry is. Now, if you had a little bit of time, you could go on further and actually find that coordinate by either completing the square or doing the negative b over 2a, and that'll give you the x coordinate. But right now we're concentrating on factoring, so if you want to try that at home, I encourage you to do so. All right, here's one other type where we're going to use algebra to solve this. Okay, we want to find the x-intercepts of the following equation. So I've used the zeros, the roots, and x-intercepts, but it's all the same thing. We set the equation equal to 0. Now notice in this case, oops, that should be a 2, I'm sorry, at home. I'm going to fix that by the time you download it. That should be a 2x squared minus 8. Notice that there is two terms, but there's a squared term and a constant. There's not a non-squared term. Well, this is a little bit different. We don't really have to use factoring here. I'm going to show you a couple ways to do this. Again, the first step is to look for a common factor if you are factoring. So here's how we do it with factoring. We'll divide out the 2, and that gives me x squared minus 4 equals 0. Now, x squared minus 4 is a very special binomial. It's a difference of two perfect squares. And that's going to factor into the product of two conjugates. So the product of a sum, x plus 2, the square root of x squared, the square root of 4, and a difference, x and 2 with a minus in there. And now I have three factors. So again, I can set each of them equal to 0. So 2 equals 0. Don't think so. Or x plus 2 equals 0. Or x minus 2 equals 0. Well, solving that, I get x equals negative 2 or x equals positive 2. So I actually do have my two roots. Now, the other way to do this is by extracting the square roots because there is no x term. There's only a square term and a constant. So the other way to do this is to separate the variables. Get your variables, in this case x squared on one side, and add 8 to get your number on the other. And I'll solve by dividing by 2. 8 halves is 4. And now I will solve for x by extracting the square roots. That is, taking the square root of both sides. The square root of x squared is x. Now here's what you have to remember. Whenever you are extracting square roots and you're finding x's, you have to extract both the positive and the negative root, which in this case is going to be x equals plus or minus 2. And those are still the same two x-intercepts that we found over here. Now to sketch the graph, what we're going to do is draw a little x and y axis. Our roots are negative 2. There's one. There's the other one. And this is a parabola that opens up. This one we can actually find the y-intercept. If I plug in a 0 for x, 0 minus 8, that's negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Just enough room down there. It opens up. That is going to be the vertex in this case. And how do we know that? Because my roots are symmetrical, negative 2 and 2. And so I know that the axis of symmetry is going to be the y-axis right in between them. Now it's time for that part of the show we call
Deja Review.
What we're going to do today is we're going to look at an application. Okay? How can we use parabolas? How can we use the fact that the vertex is either a minimum point on the bottom, or if it opens down, the vertex is a maximum point? Well, here's a nice little application. The height and the velocity of a ball that we throw straight up into the air in this case, with an initial velocity, let's say, of 28 feet per second. We're throwing it up pretty quickly. From an initial height of 4 feet, so maybe we're holding it at our waist and throwing it up. Well, it can be modeled by these two equations from physics. Here they are. The height at any given time t is negative 16 t squared plus 28t plus 4. Okay? The velocity at any given time is modeled by negative 32t plus 28. Now, the negative 16 and the negative 32 are different if you're working in meters, but they are basically due in part to the gravitational constant, which is acceleration due to gravity. It's going to be 32 feet per second squared, and we're working in feet and seconds here. So that's, of course, neglecting air resistance, affecting it on the way up or down, or a bird coming through and getting it, ooh, a ball. Okay? So these are in ideal conditions, but they do give us a nice little model, a basis that we can do some calculations for predicting. All right, so here's the questions we can answer. Now that we know what the height and the velocity is. What is the maximum height of the ball? Let me zoom out there. The maximum height, how high does it go? At what time does it reach that maximum height? How long is the ball in the air? And what's the velocity of the ball as it hits the ground? Okay? Well, how can we answer that? Well, notice that this is a quadratic. It's a t squared with a negative leading coefficient. So it's going to open down. And it has a y-intercept, when you plug in t equals 0, of 4. Now, the domain of this parabola is all real numbers. But when we're looking at applications, we want to look at something called a relevant domain. In other words, what values of t, in this case, x generally, make sense in this problem. Since we're starting this experiment, as soon as I say, I'm throwing the ball up, ready, set, go, that's when the stopwatch starts, and it starts at 0. So we're looking just for positive values of t, or non-negative values of t. So I can first of all sketch what this might look like. And let's do that right here. The parabola, I'm looking basically right here in the first quadrant, right there. If I plug in a 0 for t, that's going to give me 4. So here's the y-intercept. I know that it's going to go up and it's going to come down. So there it goes, and there it goes. Now notice I said I was throwing the ball straight up. So why did I draw it going out to the side? Well, that's because I'm measuring time right here in seconds, and on here I'm measuring the height of the ball in feet, h of t. Okay? Now this point right here is the point of interest, because that is going to be where the ball reaches its maximum height, and the x value where it achieves that is going to be the time at which it reaches that. So that's the answer to question A. Well, what is that? That's the maximum height. That's just the vertex. So remember how we can find the vertex. We can complete the square on here, or we can use the x-coordinate as negative b, which is negative 28 over 2a. And then we can plug that back in and find the height. Well, your calculator can do this too. We don't have time for me to show you today, but if you graph this in y1, and you go ahead and adjust your window to look at this picture here, you can actually find the vertex numerically on your calculator. There's a command. If you hit second trace number 3 on your TI calculator, in that sequence, there'll be a maximum key. It'll ask you for a left bound, so you scroll to the left, you hit enter, scroll to the right of the high point and hit enter again, and it should print out this right here. It'll tell you that there's a maximum, and it'll give you x equals 0.875, and it'll tell you that y is 16.25. Okay, now it's using x's and y's. We're calling it t's and h's. And so what does this mean? This means that our maximum height is 16.25 feet. That's how high the ball goes into the air. And we achieve that maximum height at approximately 8.75 seconds. And that xy coordinate is nothing more than the coordinate of the vertex. But a nice application. We know what the maximum height is. So that answers questions A and B. How long is the ball in the air? Well, let's see. If we throw the ball up, it's going to, boom, hit the ground right here. So this is the ground. The x-axis is the ground. I want to find that x-intercept. Well, we just found x-intercepts today. We have a couple of ways to do that. We can actually set this equation up here, equal to 0, and try to factor, which is going to be a little bit daunting, or we can use the quadratic formula. Again, for big numbers like this, we typically have the calculator. So to find x-intercepts on the calculator, you're going to use the second trace number 2 command. And then you're going to ask for a left bound, which is going to, in this case, be above. A right bound is below. And you hit enter for your guess, and it'll scan right there, and it'll tell you, whoops, over here, it'll tell you that your 0, it calls it a 0, is x equals 1.883. And it should give you a y value of either 0 or something very, very small that's practically 0. So what that tells us then is it hits the ground at about 1.883 seconds. Okay? And remember, we're doing this all from a theoretical model, from the safety of our little basement. We don't actually have to go outside and throw the ball in time, although we could do that to validate these results. And the last one, what's the velocity of the ball as it hits the ground? Well, all we have to do now is figure out what the velocity is, which, remember, is a little linear equation, by plugging in this time that we just found right here, 1.883. So the velocity evaluated at 1.883 is going to be negative 32 times 1.883 plus our 28. And with the help of a calculator, we'll punch that in there, and we get that it's approximately negative 32.249, and that's feet per second. Now the negative just means that it's falling. The distance between where it is and where it's going is decreasing. Okay, so it's hitting the ground at 32.249 feet per second. Almost a little bit faster, speed-wise, than how fast we threw it up into the air. So again, nice application of parabolas and using the vertex. All right, we are about out of time on today's show, but I hope you learned a whole bunch that you're going to keep practicing and getting better at. Okay, if you have any questions, give me an email. I'll be happy to answer your questions. But until next time, I'm Kevin Corpy reminding you to do your homework.